Dear students, in this video we will prove one theorem which says that the nth differences of a polynomial of the nth degree are constant and all higher order differences are 0. That means if suppose we have a polynomial of degree n and we are finding its nth differences, then that will be constant, and if we are finding n plus 1th n plus 2th differences, then all these are 0. So we have to prove this. So for this, suppose we have a polynomial f of x of degree n, then that polynomial can be rewritten as this: f of x is equal to a0 plus a1x plus a2x square plus an x raised to the power n, because we have a polynomial of degree n. Now apply the forward difference here. First forward difference, delta f of x. By the definition, this is nothing but f of x plus h minus f of x. Fine. Now substitute the value of f of x plus h. Because f of x is this, so f of x plus h is nothing but a0 plus a1 x plus h plus a2 x plus h whole square plus an x plus h raised to the power n, which is written here, minus f of x, that means as it is same values. Now simplify this. So a0 is cancelled out with a0. From here a1x they will be cancelled out. So only the left term is here a1h, which is written here. Then a2 x plus h square minus a2 x square. Take the difference of these two square terms. First take common a2 and then take the difference of these two. So what we get? 2xh plus h square. Similarly a3, here we will have x plus h raised to the power 3. Here a3 x cube. Take the difference of these two after taking a3 common. So we will get this result. Similarly the last term, a in n x plus h raised to the power n minus x raised to the power n. So here we will take this common, a n x plus h raised to the power n minus x raised to the power n. So we will get this here. After simplification, first apply the binomial. This can be written as nc1 x raised to the power n h raised to the power 0, then nc1 x raised to the power n minus 1 h, and so on, plus last term is ncn x raised to the power n minus n h raised to the power n. Fine. Minus x raised to the power n multiply by an. This, so if you simplify, this is nothing but 1 h raised to the power n this, so this is cancelled out with this. So we'll get an into this term, which is written here. This is after simplification. Fine. So up to this is okay. Now after simplification, what we get? We will get some constant term like this, then coefficient of x square, then x cube term, and so on. So after simplification, what we get? We will get this type of polynomial: b0, b1x, b2x square, where b0 is nothing but we are assembling the terms, constant terms here. For example, here this is nothing but this is after assembling all the constant term we are getting this. This is denoted by b0. Similarly, coefficient of x is assembled at one place and denoted by, say, b1, and so on. This is b0, this is b1, similarly, and so on. So here is this differences, and the last term is this an, which is from this equation here, an nc1 x raised to the power n minus h. This is your last term, which is the highest power of x, which is n minus 1. So this is written here, an nh x raised to the power n minus. So this is a polynomial after taking first forward difference. Again apply the same approach, taking second difference after simplification. So we will get this type of polynomial. We are getting a polynomial in terms of b. Again assemble the constant terms and denoted by c0. Again assemble the linear powers of x and represent the coefficient by c1. Similarly, x square and its coefficient is denoted by c2, and so on. And last term is again computed from this, the highest power of x, and after simplification we will get an n h square n minus 1 x raised to the power n minus 2, and so on. Fine. So now take the nth difference. Take the nth difference. So you can see that after, when we take the second difference, so here the highest power is n minus 2. When we will take n here, then obviously highest power will be n minus n, 0, which is written here. So here we have to apply nth factorial. So what we get? We will get the result from the last term because they will be cancelled out after taking successive differences. Only the left part is this. So what we get? An. From here you can say then when we are taking the second difference, so we are getting the term n into n minus 1. After third difference we will get n into n minus 1 into n minus 2. So that means we are getting an n minus 1 h square x raised to the power n minus 2. This is our second difference. Last term, only last term. Similarly, the after third differences, last term will be somewhere here. Last term will be this n minus 1 n minus 2 h raised to the power 3 x raised to the power n minus 3. Fine. And similarly, so the nth term, what we get? They will be cancelled out. Only last term will be this. So n into n minus 1 n minus 2, and last here is 2, here is 1, here is 3, here is 2, so here is n, so obviously n minus 1 h raised to the power, here is 3, here is 3, here is 2, here is 2, so this will be n x raised to the power n minus n, because here is 2, so here is 2, here is 3, so here is 3, here is n, so here is n. So after simplification, what we get? We get this result, an h raised to the power n into factorial n, because after simplification, simplify this can be written as a factorial n. So this is, which is a constant term, there is no x, that's why this is a constant. Now when you are finding its further another difference of n plus 1th difference, then this is nothing but, because this is a constant one, so its value at x plus h and at x, they will both same values, so that's why the same values are here, and that's why the difference will be 0. That's why the highest order difference will be 0. So this is the theorem which we have proved here. Now here is a problem. Problem is what? Problem is that suppose a polynomial is given to you, then you have to find out these differences. They need very you can say very higher computation cost. You can see that this computation is taking too much time. So to simplify the calculation process, we have a method which is known as factorial notation. So now we will use factorial notation. What is factorial notation first? So a product of the form x minus 1, x minus 2, x minus r plus 1, where r is a positive integer. This is denoted by this x in square bracket raised to the power r, and is called as factorial notation. Fine. Now here, if you put r is equals to 1, then according to this, x into x minus 1, x minus 1 plus 1, so 1 is cancelled out with 1, so we have only x, so that's why only first term, that means this term. Similarly, put r is equal to 2 here, so x minus 2 plus 1, so x minus 1, that means we have to write down only these two terms. So x into x minus 1 is factorial x raised to the power 2. Similarly, third order factorial notation is x into x minus 1 into x minus 2, and so on. Here the important thing is that here interval of differencing we have taken as 1, because here x minus 1, the difference is 1, then x minus 1, x minus 2, the difference is 1, so that's why the differencing is 1. But if suppose differencing is not 1, that may be half, maybe more than 1, so in that case these are the factorial notations. Factorial notations of first order is x, second order is x minus h. Here 1 is replaced by h, x into x minus h into x minus 2h, here h into 2h, so they are second order, third order differences, and so on. And this is the rth order difference, x into x minus h, x minus 2h, x minus r minus 1h, so this is the rth order difference. Now here we have taken one example. So what is the benefit? Benefit is that factorial notation helps in finding the successive differences of a polynomial directly by the simple rule of differentiation. So if you are finding the difference of a polynomial, then you have to just simply apply the derivation, differentiation, which is more easier in comparison to finding the difference. Fine. So here we have taken one example. Show that nth order forward difference of this factorial notation of nth order, this is nothing but factorial n. And if you are finding the n plus 1th difference of the same function, factorial notation of order n, then this will be 0. So here first we will find out the first order difference of this function x. So first order forward difference, by the definition of the forward difference, its value will be its function value at x plus h. So x plus h raised to the power n minus factorial notation of order n. This is by the definition of forward difference. Now open this with the help of this, because here differencing is h. So we have to take this, just replace x by x plus h here. So what we get, x plus h, x minus h, so x plus h minus h, x plus h minus 2h, and so on. Last term will be x plus h minus r minus 1h, which is written here because in place of r we are having n, so n minus 1h. Fine. Minus this, again use this formula and substitute the values. Now simplify. After simplification, what we get, we will get this result, x minus 1 into x minus n minus 2h nh. This is the result after simplification, which can be rewritten again in terms of factorial notation as nh. From here nh, and this is nothing but factorial notation of x of the order n minus 1. Fine. This is this. Now if you are finding again apply this factorial forward difference, then second order difference of this will be nothing but delta x of n, and this is already evaluated here. This is already evaluated here, nh this. So substitute this value here, we will get nh n minus 1h and factorial notation of n minus 2. Apply the same approach, so you will get this result. That means second order difference will be nothing but n into n minus 1 h square and factorial notation of n minus 2th order, and so on. Apply the same approach n minus 1th time. So what we get, n into n minus 1 into n minus 2 and n minus, here you can see if 2 is here then 1 will be there. If n minus 1 is there, so obviously n minus 1 minus 1. H raised to the power 2 here, if 2 is here, so since here is n minus 1, so here will be h raised to the power n minus 1 and factorial x of n minus 1, which is n plus 1. So cancel out this, so we get this term, that means factorial n h raised to the power n minus 1 x. This is the nth. Now again finding the nth order difference, apply the same approach. So what you get, you will get factorial n h raised to the power n. This will be the result, and which is nothing but a constant, there is no x here. So if you are finding another further its nth difference, so delta n plus 1, then this will be the difference of two constant values, which is nothing but 0. So that's why this. If suppose you are replacing h by 1, then what will be the result? Then nth difference of x, nth order factorial notation will be nothing but factorial n 1 raised to the power n, which is nothing but factorial n. So this is written here, and n plus 1th difference will be 0 as it is. Fine. If suppose x is replaced by some ax plus b term, linear term, then the formula is written here, an a plus ax plus b factorial notation of n minus 1. This is formula is written here, general formula. So you can use this. Now the question is that suppose a polynomial is given to you, then to find out the differences in terms of factorial notation, first you have to represent your polynomial in factorial notation. So in this example we have shown that how to convert a polynomial, this kind of polynomial, in factorial notation and then find out the differences. Fine. So suppose we have taken this example, here is a polynomial of degree 3. First we will convert this polynomial into factorial notation and then we will find out its third order difference, which is equals to 20. We have to prove this. Fine. So this will be done with the help of synthetic division. The name of the method is synthetic division, written here. The name of the method is synthetic division here. Synthetic division. So we will apply this. How to apply this? So since it's the power of the polynomial is, it's a third degree polynomial. So when we are writing this in factorial notation, so this is also a 3-degree polynomial. Fine. So suppose after converting the polynomial in factorial notation, polynomial is suppose this capital A factorial notation of x raised to the power 3 plus B factorial notation of x raised to the power 2 plus C first order factorial notation plus D. So this is the polynomial, and you can see that this is a polynomial in terms of factorial notation of degree 3. Now the task is to find out A, B, C, D. To find out these, we will apply the synthetic division. How to find out this? So we will start this. So here is the procedure. What is the procedure? Procedure is that here first you have to write down the powers in decreasing manner. Highest power is x cube, given polynomial. Its coefficient is 2. So write down here. Then its next highest power will be x2 and coefficient is -3. So write down here. Then its next highest power will be x and its coefficient is 3. And then constant is -10. If suppose for example this is not given to you, so you have to write down here 0. Fine. So you have not to miss any term. Then always start with 1 here. Write down this line here and here write down 1. And below this first term you have to write down 0. This is fixed. Then draw this horizontal line. So this 1 and 0, they are fixed. Now add these two. 2 plus 0 is 2. 2 plus 0 is 2. Now multiply 1 into 2. Multiply these two and write down here. So 2 into 1 is 2. Now add these two. We will get -1. Fine. Now multiply this 1 into -1 and write down here. So which is -1. Add these two. So we get 2. And left out this last term, which is nothing but capital D. Fine. Now increase 1 by 1. So we will get 2. Because the step size we are taking 1. That's why increasing by 1. Now 2, again start with here 0. Same 0 and 0 here. So 2, 0. So now add these two. So what we get? 2. Then 2 into 2 is, write down here 4. Add these two, we get 3. And left out again one term, which is equals to C. Then again increase this by 1. So we get 3. Again start with 0. 0, add these two. So we get 2. 3 into 2 is 6. But we have to left this term. Because you have to left, at each step you have to left one term. And denote D, C, B. And this will be obviously A. So this is your A, B, C, D. So this procedure is shown here. And we have explained. So now D, C, B and A is evaluated. So substituted these values. So what you get? You will get your polynomial in terms of factorial notation is this. This is your A, B, C and D. Now first find out the first difference, which is nothing but just simple differentiation with respect to factorial x. So 6, 3 into 2, 6, power is 2. Simply differentiation. This will be 6x plus 2. So this is the derivation. In place of x here, we are differentiating our y with respect to this. Simple. Rather than x, we are using this as a variable. Now second order derivative, this will be 12x plus 6. Again differentiate this 12. So this is the simple procedure. Fine. In the next video, we will discuss about the reciprocal factorial notation and inverse operator of delta. Fine. Thank you.